Let's get started. Welcome, everyone. We're very pleased to have you here with us today for Rock Dust, the second session of This is CDR, an online event series presented by OpenAir to explore the wide range of carbon dioxide removal solutions currently being researched, developed, and deployed, and to contextualize them for policy proposals pending and under development for New York and other states. And based in Brooklyn, New York, and I work on CDR policy advocacy for OpenAir. Quick background on OpenAir: we're a distributed volunteer network dedicated to the advancement of carbon dioxide removal solutions essential to solving the climate crisis. Our growing global community collaborates on shared open source missions essential to solving the climate crisis, and research and development, policy advocacy, and activist market development. Please check out the link in the chat, and we'd love to have you join the organization. Most of you are familiar with carbon dioxide removal, the practice of capturing CO2 from the atmosphere and storing it safely for long periods of time in the geosphere, the ocean, or long-lived products. When considering CDR as we are today and with this series, it's essential first and foremost to emphasize that CDR is not in any way an alternative to reducing emissions. We must reduce global emissions and decarbonize our economy as quickly and as completely as possible, full stop. That said, every credible climate forecast, including in very stark terms, the most recent IPCC report released this week, shows that CDR will be required at gigaton scale, billions of tons per year by mid-century to counteract those emissions that are difficult or inequitable to abate, and ultimately to start removing the tremendous excess CO2 already in the atmosphere so we can restore our climate to a safer and healthier state. If you're new to CDR, our introductory This is CDR session last week with Dr. Evan Morton, if you didn't attend, is a perfect place to start. We'll put that link in the chat, along with a link to the CDR primer, which is a great and comprehensive resource if you want to really dig in. And of course, we're here today to learn more, and we'll be continuing these sessions through the fall. Now, please meet my OpenAir colleague, Megha, who will introduce herself and today's speaker, and we'll get started.
Hey everyone, I'm Megha. I'm based in London, and I also work in OpenAir's CDR policy advocacy team, and with a particular interest in the legislative policy opportunity for California, which is my home state. So this week, we're very happy to welcome Dr. Garrett Boudinot from Cornell University to introduce us to enhanced rock weathering, or ERW, as a CDR solution. And he'll explain how rock dust as a soil amendment has the potential to remove gigatons of CO2 from the atmosphere in the coming decades. Just a couple of housekeeping notes to start. So the format is going to be a 15 to 20 minute presentation format, followed by a few prepared questions, and then we'll have some moderated audience Q&A. So please do type any questions you have for Garrett into the Zoom Q&A box. It's separate to the chat box, so just make sure you click on the one that says Q&A at the bottom of your screen. And the event is being recorded, so we'll send out the video link to everyone who registered and also post it on OpenAir's website and our YouTube channel. So on to the main event. Garrett Boudinot is a research associate with Cornell's Department of Ecology and Evolutionary Biology and the College of Agriculture and Life Sciences. He also works as a community science fellow with the American Geophysical Union's Thriving Earth Exchange and serves as a science advisor at ClimateMusic. Garrett completed his PhD at the University of Colorado Boulder on the ecological impacts of climate change after receiving his bachelor's in both geology and religious studies at the College of Charleston. So Garrett, over to you.
Thank you, Megha. Again, my name is Garrett Boudinot. That covers my background. I'm excited to be here. I'm going to go ahead and share my screen. Cool. So as I said, I am excited to be able to talk about my work here at Cornell, focusing on rock dust, ! And get a 15 to 20 minutes to share with you how the application of this readily available, relatively simple rock material in soils can actually serve as a powerful CDR strategy for widespread and permanent CO2 capture from the atmosphere through a process known as enhanced weathering or enhanced rock weathering. As Megha said, I'm a research associate at Cornell in the Ecology and Evolutionary Biology department, and working with the Dean of Cornell's College of Agriculture and Life Sciences, Ben Holton. A lot of our work is with Cornell Agritech, and we are part of a larger consortium of natural climate solutions researchers here in New York and across California in the Working Lands Innovation Center. So if you're interested in the stuff that I'm talking about today, the Working Lands Innovation Center, Agritech Tech are two good places to go and see more really exciting research on this front. So Toby did a great job of kind of setting up the impetus for CDR. I will just give a very oversimplified view of my understanding of climate change and CDR. Let's see. So ultimately, climate change is again, very oversimplified problem of carbon sources and carbon sinks. We are increasing carbon sources to the atmosphere and the ocean across our transportation, energy, construction, agriculture sectors. And those are outpacing the natural capacity of the Earth to absorb that CO2 and what we call carbon sinks. And in fact, we're decreasing the capacity of our carbon sinks through erosion, land use change, deforestation, things like that. And so to mitigate the impacts of climate change, we need to, as Toby said, actively decrease our carbon sources, but we also need to increase our carbon sinks. And that's, of course, why we're all here, to talk about carbon dioxide removal pathways. And so what I'm going to be focusing on today is one carbon dioxide removal pathway that is really focused on or comes out of a natural carbon sink, a carbon sink that exists naturally in the Earth system, but that we can leverage as a powerful tool in our portfolio of CDR solutions. And it really comes out of the long-term carbon sink in the Earth system, which is the weathering of silicate rocks. And I'm showing here in a very simplified schematic where carbon dioxide in the atmosphere rains down as carbonic acid in water, weathers silicate rocks, and then the products of that weathering ultimately enter the ocean as bicarbonate and are eventually deposited in soils and at the seafloor as carbonate like limestone. But this process that I'm showing simplified here is really critical to understanding how rock dust works as a carbon dioxide removal strategy today. And so for the next few slides, please bear with me. We're going to get into the chemistry of this process. Again, CO2 and water combine in the atmosphere to form that carbonic acid. And then the silicate rocks that we're going to focus on for the rest of my talk today are predominantly magnesium and calcium rich silicate rocks. And I'll talk more specifics of those in a bit. But the idea here is when that carbonic acid dissolves or weathers that silicate rock, it produces some silica, some magnesium and calcium ions that are free in water or in solution, and bicarbonate, which is a water-soluble carbon form. And so just in this initial dissolution reaction, we've converted CO2 in the atmosphere, a greenhouse gas, into a water-soluble bicarbonate. And you'll notice with this reaction that for every one magnesium or one calcium, because those are the 2+ positive charge, we're actually sequestering 2 carbons in the form of bicarbonate. And then given certain conditions, that magnesium and calcium will react with that bicarbonate to further precipitate out a magnesium or a calcium carbonate mineral. But that process also releases 1 carbon. And so we can either sequester 2 bicarbonates or 1 magnesium calcium carbonate with the dissolution of 1 unit silicate rock here. What's important for this as a carbon dioxide removal strategy is that this is already happening, as I said, naturally in the Earth system at a rate of about 1 gigaton CO2 per year. So if we think about global CO2 emissions at between 35 to 40 gigatons roughly CO2 per year, naturally without any human intervention, silicate rock weathering is drawing down 1 gigaton. And then relative to the permanence of this process, bicarbonate remains in water in aqueous solutions for tens to hundreds of thousands of years. And then of course, if it precipitates out as a carbonate mineral, that can be stable for millions of years. And so this is an incredibly stable, permanent carbon sink that is naturally occurring. And I want to just highlight again that the ultimate fate of these rock weathering products, bicarbonate and carbonate, even if it occurs, even if the rocks are being weathered on land, they are traveling into the oceans and precipitating out as minerals there, with a smaller portion precipitating in soils. And so understanding this natural process, we can imagine that if we increase rock weathering using some specific land management strategies, we can draw down CO2 from the atmosphere on top of the natural processes and store it again for tens, hundreds of thousands, even millions of years. And the primary way that our group does that is by applying silicate rock dust to croplands to enhance that rock weathering. So that natural process, we're able to enhance the rate of it by applying pulverized silicate rocks. And here I'm showing a picture of our group doing that out in California as part of, again, that larger Working Lands Innovation Center. And the chemistry, the mechanics here are identical to what I described earlier. These are magnesium and calcium rich rocks that, by changing the aqueous chemistry of the soil solution, will precipitate out magnesium or calcium carbonate, or lead to carbon dioxide being soluble in water as bicarbonate. And so I guess the first question we often get is, why croplands? Why agricultural lands specifically? And the main reason is it's kind of low-hanging fruit. The global land surface is 37% of that is agricultural lands. Over 10% is croplands specifically. Another over 25% is pasture lands. And so these are lands that are actively managed by humans. And for croplands, we already have the equipment to spread soil amendments like rock dust on these soils. We're already spreading fertilizers, often even other mineral amendments like liming. And so this is something that most farmers and soil managers are aware of, the general practice of applying things to soils in places like croplands. In addition to the ease of implementation that croplands allow, we found that rock dusts also provide a number of co-benefits for agriculture writ large. And so these rock dusts, though they're rich in magnesium and calcium, they also provide a number of micro and macronutrients that are beneficial for crop yield overall. Those are things like the magnesium itself, but also potassium, iron, phosphorus. The change in pH that is mediated by the release of these ions from the rock dust can improve nutrient retention of soils, particularly of highly acidic soils, like those that we find in the tropical regions that are responsible for feeding a large portion of the global population, and under the status quo are very nutrient deplete. So by adding rock dust, we can increase the nutrient retention, which has huge benefits for our global food supply. There are preliminary results that suggest that there may be benefits to reduced N2O emissions from soils, again, probably mediated by that impact of pH on these agricultural soils. And for every one N2O, that holds about 250 times the global warming potential of CO2. And we're finding that N2O emissions are a major greenhouse gas from agriculture. So anything we can do to reduce that would be really beneficial for global climate as well. The silica from those rock dusts are very beneficial, we found, across crops for resistance to disease, drought, wind. All of these things that we might expect would also increase overall climate resilience of agriculture. And in addition, the minerals provided by rock dust may also protect organic carbon from degradation. And since I mentioned that, I want to take a step back. I've got in the white box there at the bottom, and just remind that though I'm talking about the addition of soil amendments for carbon benefits, enhanced weathering itself does not directly contribute to organic carbon. What we're talking about is a more stable, more thermodynamically stable form of inorganic carbon, that bicarbonate or carbonate minerals that again enters for the bicarbonate waters whose fate is ultimately the oceans. And so measuring it is much more different than measuring organic carbon. Thinking about how it works with overall agronomy is much more different. Although again, there may be some co-benefits with rock dust, enhanced weathering, and some of that organic carbon sequestration. So now that I've kind of covered why rock dust may be beneficial for climate and for crops, I think it's important to discuss where exactly we get the rock dust, that supply and question, to understand the overall life cycle of this carbon dioxide removal strategy. So here I'm showing one map, but there are many maps to try and estimate the global distribution of ideal geologic substrates to provide, again, the ideal chemistry for this reaction. And they're displayed in red on this map. You see they're really widespread. These are rocks that are rich in calcium and magnesium. What we look for specifically with croplands are rocks that have low to no levels of toxic heavy metals, of course, to protect the crops and the people consuming the crops. That's really important. We need these rocks to be easily accessible for farmland so that they're not being transported over large distances, contributing to a larger carbon footprint of this practice. And that small grain size is really important. That's why it's pulverized, it's rock dust, not applying large chunks of rock, because it's the completion of that weathering process that drives this, this strategy, and that's dependent on grain size largely. And what's good news is that we can meet a lot of these criteria by tapping into existing reservoirs of mining byproducts. In other words, existing mines, many of them and locations that are shown in red on this map, that look for other minerals and other rocks, and in the process are grinding up a lot of the geologic substrate and having to store it somewhere. A lot of those stored pulverized rock powders happen to have ideal chemistry for this project, for this process. And those are the ones that at least our group is really focusing on right now. So I've got some pictures to kind of give a better sense of this. So on the left, I'm showing some of the powdered rock dust that was shipped to one of our research fields here in upstate New York. We ship it by the ton and it's just kind of dropped off in these piles. I kind of zoom in the middle there so you see me holding it. The larger clumps are really just the fine grain powders that have clumped together in the moisture. And you can kind of see my fingers in that middle picture are coated with some of the finer stuff. So this is distributed over a range of grain sizes. We find generally on average, they're about 100 microns. And then on the far right, I'm showing after we've incorporated that rock dust into the soil, I picked up a clump of the soil and you see the gray rock dust blending in with that brown lima loam soil that we're working with up here. And so it mixes into the soil readily because of its grain size and again, ultimately dissolves. So this is the kind of the background of rock dust as a climate solution. But I think it's helpful to put some numbers on this. So in preparation for this, I just ran some simple literature review and simple back of the envelope calculations to give a sense of the power of this strategy. It's important to note that enhanced weathering as a climate strategy is relatively new scientifically. It's been theorized for a while, but in terms of experimentation and demonstration on the field scale, it's very new. And again, that's one of the things I want to highlight today is the need for continued research and optimization in this to actualize its potential. But within the range of models and experimental results, we do have some general agreement of the power of this. Again, depending on the type of rock, the soil, grain size, and things like that. And so one example we like to use is a mesocosm study that showed about 1 to 4 tons carbon dioxide removal per hectare. So to put that into a global context, of the amount of land we have in agriculture and the amount of CO2 that could scrub up. Here I'm showing results of, again, a very simple back of the envelope calculation of scaling up that CDR potential of rock CDR in gigatons CO2 per year. And I'm showing each of those, the 1 ton, 2 ton, 3 ton, and 4 ton CO2 per hectare rate, which is something that can be optimized. If we start on the left, we see that the amount of US cropland, if we can reach that top level, that maximum level from this one study of 4 tons CO2 per hectare, that could get us to about 1 gigaton carbon dioxide removal per year. Again, that's on par with the rate of natural carbon sequestration from rock weathering using US croplands alone. And when we think about the US CO2 emissions of about 6 gigatons per year, that's a significant offset that we could actualize if this relationship holds. If we scale that up to global cropland, we could get almost 5 gigatons CO2 removal, which would almost offset the entirety of US emissions. As I mentioned earlier, global pasture land is much more extensive. And so if we can figure out a way to easily spread rock dust on pasture lands as well, as you can see, it really accentuates the potential carbon dioxide removal from rock dust. And so again, we don't think that global pasture land, and certainly not global agricultural land overall, is ripe for this. I believe that certainly there are places where this strategy might not even reach 1 ton carbon dioxide per hectare. There may be instances where we can exceed that 4 ton CO2 per hectare. Again, and that really comes out of the early stages of research and development from the existing science now, highlighting on that slide significant uncertainties. Knowing that a number of folks here are in New York State specifically, I wanted to also see, well, how would this look on a regional scale? So if we zoomed in far on the bottom left of this plot, we would see here the amount of New York farmland in the dotted line intersecting with the x-axis at about 7 million acres. And the New York emissions at just over 200 million tons. And what, again, from the existing research shows is that this may, if deployed across New York farmlands, be able to offset about 5% of New York's greenhouse gas emissions. And so, again, within the portfolio of carbon dioxide removal strategies, this is one that could easily scale up given the infrastructure needs and existing infrastructure, and one that could have significant impacts on our global emissions. But to highlight the uncertainties, I want to be very clear of where we are. There are a number of relationships that we're still understanding and trying to optimize to actualize the strategy. For example, we know that rock dust and rock dust weathering and its role in changing soil and water carbon is strongly dependent on soil texture, soil mineralogy, soil chemistry and pH, the organic matter in the soil, the microbiome of the soil. All of those together impact the weathering and chemistry of this process differently. Similarly, the climate, the temperature and moisture specifically have a strong impact on this process. And in addition, the types of crops, the cropping styles, all of these play a really important role on how this process works. And it's critical that we understand the science of this as we deploy it widely. And once we understand these relationships, then we can begin to answer some important questions about scaling up this strategy, including what are the real maximum rates. So I said, from that one study, 4 tons per hectare, that was based on one type of mineral and one type of soil. And again, we know based on the mineralogy in the soil, it can be quite different. Once we understand that, how can we optimize it? In what instances might we be able to exceed those maximum natural rates, perhaps by synthesizing specific soil silicate amendments? What are those other agronomic benefits? And what are some unintended risks that might come from this, either immediately over the long term? These are things that our group is working on understanding with large scale, long-term enhanced weathering demonstrations. I mentioned earlier the differences between this process and organic carbon in soils, and that has large implications for how we monitor, report, and verify this carbon sequestration strategy, which is absolutely critical for making sure that this is an economically feasible strategy for those who implement it, and making sure that it actually does has the benefits that we want for the climate. And then finally, once we understand that, how can we implement economic and policy incentives to ensure that this is done safely, this is done responsibly, and that this is done effectively at the scale we need for it to be part of our portfolio of climate solutions, regionally, nationally, and even globally. And so I'll just wrap up by showing a couple pictures of our research plots here in upstate New York, where we're working across a number of crops in different rock amendments, doing very intensive constant monitoring of the soil chemistry, the soil structure, soil water, and its interaction with the crops, so that we can better understand those and other climates that we're studying here in New York and in California, work with the stakeholders that we partner with to understand how we can answer some of those important questions from policy and economics to agronomic practicality, and then scale this up at the rate we need. And so with that, I'll finish up just with the main takeaway that enhanced weathering with rock dust, at least in agricultural soils, is a potentially gigaton scale permanent carbon dioxide removal strategy. But again, it requires continued research and optimization. So I think we've got plenty of time here for questions. Thank you.
Thank you. That was amazing. And we do have a tremendous number of questions in the audience chat and Q&A, which is fantastic. We have a couple quick prepared questions that we wanted to get out there, and then we'll, Megha is gonna take over and pick up some questions from the Q&A. First of all, so there's this recent paper that was published by a couple of authors, Shannon Osaka, Rob Bellamy, Noel Castry, entitled Framing Nature-Based Solutions to Climate Change. And it really resonated with us at OpenAir with its argument that we need to move beyond the sometimes or even often polemical labels of nature-based versus technological or engineered CDR solutions. And focus on given solution's specific characteristics, scale potential, co-benefits, potential negative impacts, and really critically additionality, life cycle analysis, and permanence. ERW rock dust, as you described it here, is certainly nature-based, but it's also engineered. So I feel like that's like a great kind of bridge that maybe can help us get over this argument. Do you have any thoughts on that? And do you agree with that general premise that we need to get beyond the labels and more into like what these solutions actually do?
I definitely agree with that premise. As you mentioned, this is we do often think of this as a technological solution because of, on one hand, the need to be strategic and scientifically minded, and in a sense, engineer how we do it, from the materials that we're using to how they're applied, the rate at which they're applied. And then on the other hand, how we monitor it, because again, it is so different. And that's really where the science is rapidly accelerating now, is better understanding that. And so these are technological questions. But on the other hand, there was actually some of our colleagues here at Cornell recently published a study that did a social survey and found that the public was much more supportive of some of these natural climate solutions, and specifically in their study, soil-based solutions, than other kind of larger geoengineering solutions. And so there is some balance that I think we need to strike between what the general public can understand or appreciate about some of these, but then also what our biases might be towards them, and make sure that, as you said, we're focusing on things that can scale, that can be permanent and additional, rather than things that sound nice but might not actually have the benefits that we desperately need to address our climate.
Awesome, perfect. Number two, I'm going to conflate two questions because you guys do work in both California and New York. And based on one of your slides, it sounds like rock dust, enhanced rock weathering have potential megaton CDR scale per year in both of those states. California will be more since they're more agricultural lands, but where, like in terms of, I know it's very difficult to predict, but like what kind of timeline do you think we might be on for commercialization? There was recently a purchase in the Stripe purchases of I guess a field trial for rock dust enhanced rock weathering on forested lands in the UK from the Future Forest Company. But where do you think we are, like potentially in terms of being able for whether it's a voluntary carbon market purchase of the CDR or potentially future state procurement of CDR? Like how far off are we?
Sure, I'll address two parts of that. So on one hand, I do want to address, we're really getting some interesting information by comparing California and New York now, where my colleagues out in California have been doing their trials for several years now, and we're just starting up in New York. But already we can tell that just based on the differences in climates, we're getting very different enhanced weathering practices. So for weathering, of course, water is a primary need. And so it might in fact be that in California, there are more limitations to this process than we would have in New York. And I think that really understanding how climate geography distance to the ideal geology, how all of these things impact the efficacy of this practice. We really need to nail that down before we start selling this as a widespread commercial practice for farmers. And that kind of feeds into the second part of that question, getting more directly at commercialization of what's already being done. I know some of my colleagues have spoken with the folks at the Forest for Futures, and really where we land on the thoughts on commercialization is that it really needs to be based in the science. And right now we're just seeing so much heterogeneity, so much variability in the response to different soils, crops, climates. I've looked at some of the companies that are already selling rock dust for enhanced weathering, and they're making claims that are hard to justify with such variability in their potential customer base. And that's really where the monitoring, the reporting, and the verification needs are. And again, because this is so different, the primary carbon dioxide removal pathway may be through bicarbonate, which is something that's in water and constantly moving out of the system. So it requires a very different monitoring and verification strategy than organic carbon, for instance, or than no-till practices. We really need to address this and come to some science-based consensus before we start, again, selling this as a strategy that folks can take where we know it's not going to work the same everywhere.
Got it. That's great. Megha, do you want to kind of start pulling in some of the questions from the audience since we have so many great questions here?
Yeah, sure. We do have a bunch of questions. I'll try to combine some of the similar ones. So the first one is a bit of like an activist kind of angle on it. So the question is, to my knowledge, there are over 35 rock dust companies in North America. How can we mobilize everyone and get everyone on the same page to maximize our lobbying power, promotional power, work out the carbon credits for farmers, and basically just get the maximum of this rock dust into the soil?
That's a great question. I'll give a plug for the Working Lands Innovation Center again, because I think what's really important about the work that we're doing through that center is engaging a wide range of stakeholders. And so that is mining companies and industry and folks who are selling the rock dust. It's also importantly farmers, folks who would need to acquire the rock dust, apply it to their soils, which is their livelihood and their generational livelihoods. with policymakers, with folks who are on the carbon credits accreditation side of things, even with tribal partners, to make sure that the folks who are going to be implementing this are getting the benefits out of it that we know they deserve for taking on this CDR strategy that then the rest of society benefits from for its climate for its climate impacts, but again, also making sure that it's economically viable for them and creates something that can push the levers, scale up at the level that we need. So I guess the short answer of that, at least from our perspective, is really engaging a wider range of stakeholders, of which, of course, industry is a major player.
Cool. The second question, which we got a few times, I think, so I'll try to read through a few ones that touched on this, but it's basically about kind of the sourcing. So do we know what kind of mining operations are the best with the most volume of byproduct to supply rock dust? So, you know, metal versus gold versus quarry. Kind of related questions we also got were, have you been looking into industrial byproducts like from cement manufacturing to get rock dust, we don't have to crush as much? And bonus question, are you considering the paramagnetism of those rocks? And could basalt from waste mining be used in the weathering process, avoiding the cost to crush the rocks?
Yes, I will answer those not in the order. So the last one there, that's exactly what we're doing. With many of our trials, we are working with already crushed basalts that are again existing as stockpiles of byproducts from mining operations. They have an ideal calcium magnesium chemistry, again with low levels of those toxic heavy metals, and that's what we're working with. To be blunt, that's low-hanging fruit. That is existing and it's out there, and it's something that can have, again, powerful climate impacts without, as the question asker referenced, needing more energy for crushing. And then we are also working with some engineers here at Cornell on ways that we can post-process some of those industrial waste products to be viable for croplands for enhanced weathering. Again, the main concern being we want to mitigate against any contamination. So I know for many of these industrial products, things like nickel and chromium are in high concentrations in those. We want to make sure that we're pulling that out before we're applying them to crops that then might end up into our food system.
Great. We got also a couple of questions basically asking about how this would affect ocean acidification. Like if there's runoff from these processes, would it increase alkalinity, increase acidity? What's the impact there?
Glad that was asked, because that is certainly important downstream impact of this process, that adding alkalinity to the oceans, again, by percolating through groundwaters, entering surface waters, and flowing into the oceans over long term, that certainly should buffer against ocean acidification. And there are several studies that have modeled the impacts and show that at scale, this could play an important role in mitigating the already occurring impacts of ocean acidification, which is a major concern with climate change in the oceans. And some of our researchers are actually working on geospatial modeling approaches to really understand, okay, once bicarbonate is produced in our field trials in New York, what happens to that bicarbonate? What's the residence time of it to get to the oceans? And how much of it actually remains as bicarbonate by the time it gets to the oceans versus perhaps precipitating out as carbonate en route? So we understand the first order relationship and are optimistic, but again, there are some important scientific questions that need to be answered before we can make any quantitative claims on that.
Makes a lot of sense. We also got a question about, which is I think pretty open-ended, but where could digital solutions be deployed to scale up ERW?
Yeah, so that's interesting. I will just say again, monitoring this is one of the more of the soils, the soil waters through the growing season to really capture at snapshots through time of the changes in soil chemistry and carbon sequestration before it again flows away into surface waters and leaves where we're growing the crop specifically. And so I think that is itself a huge area for advancement and for potential synergies between the growing agricultural tech industry and what we're doing. And any ways that we can accelerate the rate at which we measure things like alkalinity. There's so much work going into measuring soil organic carbon quickly. That's great. And I know that there is similar work, at least from a scientific perspective, trying to accelerate the rate at which we can monitor the inorganic side. And we think that's really important for this process.
Cool, great. And that actually answers a couple of the questions we got around the challenges of measurement and certifying, which is great as well. Cool, I'm just gonna close with one last one. What is the need for rain or irrigation in the CDR method? And would a rainy ecosystem be ideal for deployment, and can it be done in forested areas?
So to the first question, yes, more rain is better. This is a weathering process. And so in very arid conditions, just first order kinetics indicate that you're not going to get the rate of weathering. And so it's going to be a slower process. And again, testing some of our trials in the Imperial Valley of California compared to here in upstate New York, we can already tell you that we're getting very different enhanced weathering outcomes. And then on the second side there with forests, certainly we focus right now on croplands because of the existing equipment and the ability to scale up. But certainly there are lots of other opportunities to actualize this strategy. I know of some groups that are applying some of these minerals on coastlines where we can weather some of this and directly add alkalinity to the oceans. It was mentioned earlier, the Forests for the Future folks who are working on this in forests, which is certainly a possibility. Again, the question is, how do we spread it out there at the rate of rock dust per acre required to see the carbon benefits without having a large carbon footprint? And we were even talking before the session here about opportunities on turf grasses. And I mentioned earlier pasture lands as opposed to cropland. So I think to getting to that first question, if there's water and suitable rock dust available, this is something that we can and should see if we can get it as widespread as possible to have those climate benefits happen.
Amazing. This has been great. Thank you so much, Garrett. I mean, I feel like we may have to have you back because I feel like we could go another hour with all the great questions in the Q&A. But we're going to close now, and I just want to share my screen real quick about next week's session on biochar with Kathleen Draper from the International Biochar Institute. And Garrett referenced a couple of other mineralization related CDR solutions. We are going to have Project Vesta in October. They talk about coastal enhanced weathering, which is sort of tangentially related. Matt Eisenman from Stony Brook University has an ocean alkalinity enhancement solution that again relies on the carbonate cycle that again touches on this. So we have a lot of cool stuff coming up, and Garrett, again, we may have to have you back. Thank you so much. These are the other ones we have coming up. We have Ocean CDR on the 24th. I mentioned Matt on the 7th, and then we'll be doing these weekly through the fall. Thank you again, Garrett. It was really fantastic presentation and discussion. Thank you, Megha, and thank you all for joining.